You know, in the world of trigonometry, some graphs are pretty strange. They have these invisible walls, lines they get super close to, but they never ever touch. Today we're going to be detectives and figure out exactly where these walls are hiding for the tangent and cotangent functions. Let's dive in.
It all comes down to this one kind of forbidden idea in math, right? What happens when you do the one thing they always tell you not to do? Divide by zero. Well, the function doesn't just give up. It throws up a wall, a massive, infinite barrier. And our mission is to figure out exactly where these walls are.
Now, in the math world, these walls have a proper name, vertical asymptotes, but I like to think of them as crime scene tape. It's a boundary the graph can get right up against, but it just can't cross. And the number one clue is always this. These walls only pop up when the bottom of a fraction, the denominator, hits zero. That's our trigger.
So, let's crack open our first case file, the tangent function. We've got to understand its secret identity before we can find its weaknesses, its walls.
And there it is. The big secret isn't so secret after all. Tangent is really just a fraction. Sine of x divided by cosine of x. This little ratio right here, it's the key to solving this whole mystery.
Okay, so knowing what we know now about those vertical asymptotes, this leads us to the most important question of all. Where does this thing actually fall apart? Where are the invisible walls?
You got it. The whole structure just breaks down the second that denominator, cosine of x, equals 0. That's the exact moment the tangent function shoots off to infinity and creates one of those walls. So all we have to do is find all the spots where cosine hits 0.
And if you think back to the good old unit circle, you'll remember that cosine is the x-coordinate. So where on that circle is the x value 0? Well, straight up at the top and straight down at the bottom. That happens at pi over 2, 3 pi over 2, 5 pi over 2. You get the idea. It just keeps going forever. And boom, we found our wall locations.
Now, here's something really interesting about tangent. Look at how often this whole pattern repeats. You know how sine and cosine take a full 2 pi to do their thing? Well, tangent is a little more hyperactive. Its period is just pi. That means its whole S-shaped curve and the walls around it repeat every pi units. It's basically happening twice as fast.
All right, case file number 1 is officially solved. Let's move on to case file number 2. We're going to investigate tangent's closest relative, cotangent. It uses the exact same logic, but you're about to see how one tiny change flips everything upside down.
See, cotangent is literally the flipped or reciprocal version of tangent, cosine of x divided by sine of x. And that one little flip changes everything. The new weak spot isn't cosine anymore. Now, this function breaks whenever its new denominator, sine of x, is 0. This table lays it all out pretty clearly. Since their denominators are swapped, their walls are in totally different spots. Tangent has walls where cosine is 0, but cotangent's walls show up where sine is 0, at 0, pi, 2 pi, and so on. And check out their shapes. They're mirror images. Tangent is always climbing uphill, while cotangent is always sliding down.
Okay, now that we've got the basic rules of the game down, it's time to crack the code on some more complicated cases. What happens when we start stretching, shifting, and squeezing these graphs? Let's walk through a few examples.
All right, first up, y equals tangent of 2x. That 2 on the inside of the function acts like a compressor. It's squeezing the graph horizontally. So where are the walls now? The logic is exactly the same. The function breaks when its input is at one of the bad spots. We know the bad spots for regular tangent are at pi over 2 plus any multiple of pi. So we just take our new input, which is 2x, and set it equal to that. Then do a little algebra, just divide by 2, and we find our new walls are at pi over 4. And because the graph is squished, they now show up every pi over 2 units.
Now this one is a classic trap. You might look at it and immediately think the graph shifts pi to the right. But wait, to see the real horizontal shift, you have to factor out that coefficient in front of the x, which is 1/2. It's kind of like putting on X-ray goggles. Once you do that, you see the true parameters. The period is pi divided by our b value of 1/2, which means it gets stretched out to 2 pi. And now you can see the real phase shift inside the parentheses, a move of 2 pi to the right. Always remember to factor first.
Okay, for our last example, we've got 3 transformations all at once. The minus pi over 4 shifts the whole thing to the right. So our original walls at 0 and pi just slide over to pi over 4 and 5 pi over 4. Easy enough. But the really cool part is that negative sign out front. It acts like a mirror and flips the entire graph upside down. So, instead of that classic decreasing slide you expect from cotangent, this graph is now an increasing curve between its new walls.
So there you have it. The case is cracked. These invisible walls aren't random at all. They're just a direct result of that one golden rule. You can't divide by zero. And every time you stretch, shift, or flip the graph, you're just leaving more clues to find their new locations. You got the detective's toolkit now, so are you ready to go find your own invisible walls?